the most common customer complaints heard in the truck service business are those about drivetrain vibration. Frequently, they can be some of the most difficult and time-consuming to diagnose and treat. The purpose of this program is to familiarize international servicemen with the causes of drivetrain vibration and to teach them a step-by-step diagnosis and correction procedure. Anyone who drives a truck should be aware that any obvious drivetrain vibration is an indication that something is wrong with the vehicle. If it is not corrected, the vibration can lead to extensive damage in other parts of the vehicle. Drivetrain vibration can be caused by one or a combination of several discrepancies located almost anywhere on the vehicle. Vibration can be caused by components that are loose, bent or broken, worn out, misaligned, or out of balance. Problems can originate in the brake, wheel, and tire assemblies, in the front suspension, rear suspension, the engine or its accessories, the transmission or parking brake drum, the U-joints, propeller shafts, center bearing, or companion flanges, or within the differential, axle, or wheel bearings. As you can see, drivetrain vibrations can be very difficult to isolate. Therefore, it's logical to use a step-by-step troubleshooting procedure that begins with the most common and obvious problems and proceeds to the most complicated and involved. A chart outlining the troubleshooting test procedure is included in your reference guide. First, thoroughly interview the operator. Often, he may have an idea what the problem may be. Examples of questions he should be asked include: when does the vibration occur? At what RPM range? Does it occur under load or when coasting? Then inspect the vehicle for obvious defects. Look for broken or loose cross members, broken or loose engine and transmission mounts, defective suspension torque rods, spring U-bolts, or propeller shaft U-joints. Any obvious defects should be corrected before you proceed. Next, check and adjust tire pressures for the load being carried. If the tires are cold, you can inflate them to the required pressures. If they are warm, the only thing you can do is equalize the pressures. If the unit is not equipped with a tachometer, install a portable tach. It will be used during the test procedure to determine the RPM range in which the vibration occurs. Next, put the transmission in neutral, set the parking brake, and operate the engine to its maximum recommended RPM with the clutch disengaged. If an unusual vibration is present, it will be necessary to perform the engine and accessory checks. First, make certain that the engine is performing satisfactorily. If you feel there is an engine problem, diagnose and correct the problem with conventional engine troubleshooting procedures. If the engine is operating properly, the next step would be to check the engine and transmission mounts. Check to see that they are properly secured, that the rubber insulators are not compressed too tight or damaged, and that there is no metal-to-metal contact. If the mounts are defective, they should be repaired and the vehicle tested before proceeding with the inspection. Next, check the exhaust system components and their mountings to make sure they are intact and positioned correctly. Loose baffles in a muffler could also be the source of a complaint. Make any necessary corrections and test again. If the vibration persists, operate the engine at the critical RPM and visually check the operation of each engine accessory. Be certain the air compressor, freon compressor, power steering pump, and alternator are loaded, performing their function, while you observe their operation. Test the internal operation of the accessories by disengaging one accessory at a time, and then test the result. Repair or replace any defective unit. If the preceding accessory checks have been performed and the vibration still exists, the problem may be the vibration dampener, crankshaft, flywheel, or clutch pressure plate. These components must be removed and tested on a dynamic balancing machine. In some applications, the vibration dampener and/or flywheel cannot be checked without the crankshaft and reciprocating bob weight assemblies. Your local dynamic balancing specialist can help you determine the best way to check the balance on the specific engine being diagnosed. If there is no vibration with the transmission in neutral and the clutch disengaged, Slowly release the clutch and raise the engine RPM to its maximum recommended speed. If a vibration is detected, the problem is in the clutch disc or transmission. Remove each component in order and test to isolate the cause of the problem. Review the preceding information by completing exercise number 1 in your reference guide. Start the projector when you have finished. If static testing doesn't bring about the vibration, road test the vehicle. In many cases, this is the only way the operator can demonstrate the complaint. Don't cut this step short. It is extremely important that you actually experience the complaint and are able to duplicate it. It's important that road testing be done under actual operating conditions. Often a load or type of load, trailer or type of trailer will influence a disturbance. For this reason, don't bypass this very important step, even though it may be inconvenient. While out on the road, test the vehicle in a combination of transmission, auxiliary transmission, and multi-range rear axle speeds. Record the engine RPM, gear selection, and road speed at which the vibration is felt. If the complaint is detected in one particular gear selection, such as third gear in a 4 or 5-speed transmission, the trouble is probably in that component. A visual inspection of the inside of the component will usually disclose the problem. In cases where the vibration is detected only in the higher gear selections at higher engine RPMs, it is unlikely that the problem is generated within the geared component. This is only if the complaint was not noticeable at low speeds. Should loading, acceleration, or deceleration have an effect on the vibration, the cause is most likely in the propeller shafts and associated parts. If the disturbance is felt through the steering wheel, thoroughly inspect the front suspension, steering gear, and steering linkage. Then check the wheel ends and bearings. One quick check is to preload the front wheel bearings to 15 pounds torque with a dial reading torque wrench. Slowly rotate the wheel while maintaining wrench loading and observe the dial indicator. If there is bearing surface damage, the indicator will jump sharply. If this test is not possible, the bearing assembly should be removed and visually inspected for abnormal wear or damage. Remember to road test after any front-end repairs are made. After you are certain the steering linkage and bearings are not the cause of the disturbance, check all the tires for chunking and signs of ply separation. Check all the wheels for cracks or damage to the center sections or rims. Next, check each tire's tread runout. The runout should not exceed 3/32 of an inch. Then check the lateral runout at each tire's sidewall and outer rim edge. The maximum allowable side-to-side runout is also 3/32 of an inch. Retorque or replace any wheel tire assembly that is out of specifications and road test the vehicle. If the disturbance continues, raise the chassis and support the front and rear axles on safety stands. In some cases, the safety stands will dampen the vibration from the rear axle. It is often necessary to raise the vehicle off the rear axle stands a slight distance and support the rear of the vehicle with safety stands positioned under the rear of the frame. Extreme caution must be exercised when the vehicle is operated in this situation. If the complaint seems to come from the front end, in which case it should be felt through the steering wheel, check the front tires by spinning them on the truck or on a dynamic tire balancing machine. If they are out of balance, dynamically balance them and road test the vehicle to confirm the repair. If the vibration seems to originate from the rear axle, very carefully spin the rear wheels up to the critical RPM using either the engine or a wheel spinner, shown here, to confirm the location of the problem. Then remove the rear axles and repeat the test. If the problem is no longer evident, the trouble lies within the wheel tire assemblies, hubs, or brake drums. If the problem still exists, it is a propeller shaft, transmission output bearing, or differential problem. Isolate a problem in the wheels, hubs, or brake drums by reinstalling the axle shafts and removing the wheels. Then spin the hubs up to the critical RPM. If the vibration disappears, the rear wheel should be dynamically balanced and the test repeated. Should the vibration still persist, Check for looseness or rough operation of the rear wheel bearings. If the bearings are suspect, inspect them and replace the defective parts. Retest the unit to confirm the repair. If that doesn't solve the problem, check the brake drums and hubs for excessive runout and balance, according to the procedures outlined in Truck Service Manual CTS 2045. Review the preceding troubleshooting steps by completing exercise number 2 in your reference guide. Start the projector when you have finished. When the vibration continues with the axle shafts removed, the propeller shaft and its related parts should be checked. The propeller shaft assembly includes the transmission companion flange, universal joints, center bearing, slip yoke, propeller shaft tubes, and rear axle companion flange. First, inspect the U-joints and replace any that are damaged, frozen, or worn out. Check the center bearing and its mounting to make sure it is secure and in good operating condition. Inspect the input and output shafts of each drivetrain component for excessive radial movement. If any of the bearings are found bad, repair them and retest the unit. If all the parts are in good condition, check to see that the U-joints on each shaft are properly aligned. On each propeller shaft, each yoke must align with the other. If they are misaligned, align them properly and retest the unit. Should the complaint persist, rotate the slip yoke 180 degrees on the propeller shaft and test your results. If the vehicle is equipped with a 3-shaft driveline, rotate the center shaft 180 degrees and retest the unit. If that has no effect, and the unit is equipped with a driveline brake, remove the drum and repeat the operational test. If the drum is the problem, it should be dynamically balanced or replaced. If this service is not available, an alternate method is described in Truck Service Manual CTS 2045. Excessive companion flange, yoke, and/or propeller shaft runout can also create a vibration problem. When measured with a dial indicator, radial runout must not exceed 5/1000ths of an inch at the companion or adapter flanges or yokes, 10/1000ths at the tube end welds, and 15/1000ths at the center of the tube. Remember to clean the various parts before taking the dial indicator measurement. Replace any component that is out of specifications and retest the unit to see if additional troubleshooting is required. The next area requiring attention is propeller shaft angular analysis. There are 2 types of driveline arrangements that will satisfactorily transmit power: the parallel joint type and the non-parallel or broken back joint type. The parallel joint type requires that all companion flanges and/or yokes in the driveline are parallel to each other. When this is true, the working angles of the U-joints, shown as angles A and B, are equal and opposite the center line of the propeller shaft. For example, if the engine transmission output shaft is 5 degrees down from a true horizontal plane at the rear, the center line of the driven shaft of the auxiliary transmission or differential must be 5 degrees up. With the non-parallel joint or broken back type of driveline, used only on some tandem axles, the U-joint working angles, shown as angles A and B, are equal, but the output shaft centerline and driven shaft centerline are not parallel. The working angles of both joints on a given shaft must operate at the same angle, with not more than 1/2 degree variation. If the U-joint working angles are not equal, a vibration will often result, and the life of the U-joint will be extremely short. The first step in determining the working angles of the U-joints is to record the engine transmission declination, or slope angle to the rear. For this operation and the following checks, you will need a magnetic-based protractor, SE 2067, or an ordinary machinist's protractor. With the vehicle on the ground and loaded, place the protractor on a clean machined pad on the engine that is parallel to its center line. Record the angle for computations later on. Next, measure the propeller shaft angle and record it. Then, remove each shaft from the vehicle and measure the output shaft flange angle. Do this by placing the flange in a vertical position, placing a flat plate over the clean, undamaged flange face, and reading the protractor. The reading should be 90 degrees minus the engine angle recorded earlier. In this case, the engine angle was 3 degrees, so the protractor should read 87 degrees. In an application where a yoke is used, the alignment can be checked by turning the yoke to the vertical position and placing the protractor on top of the yoke and in line with the engine. The reading should be the same as the engine angle recorded earlier. In either application, the results should not differ more than 1/2 degree from the engine angle. If it does, it suggests that the yoke or flange is distorted or the engine and transmission are misaligned. Flange or yoke distortion can be determined by rotating the flange or yoke 180 degrees and taking a reading with a protractor. If the reading varies more than 1/2 degree from the previous reading, the flange or yoke is defective and must be replaced. If the reading does not vary, the engine and transmission are probably misaligned and should be repaired according to instructions outlined in Truck Service Manual CTS 2045. The same procedure should be used to determine the angle of the next input or output shaft in order. Note that when checking shafts going through a center bearing, the shaft angle must not vary more than 2 degrees from the bearing angle. Adjust any bearing that is out of specification. In a parallel joint driveline, the driven shaft centerline angle must not vary more than 1/2 degree from the output shaft centerline angle. In this case, the engine centerline angle is declined 5 degrees to the rear. Therefore, the driven shaft centerline should be inclined 5 degrees plus or minus 1/2 degree to the front. Should the driven shaft be out of specifications, the component must be shimmed to the proper angle. If the component is a single rear axle, caster shims can be installed between the axle's spring pads and the springs. If the vehicle is equipped with tandem axles, their operating angles will be controlled by the length of the torque rod that extends from the top of the axle to the vehicle's crossmember. Varying the torque rod lengths will accomplish the same thing caster wedges do on single axle units. Non-parallel drive lines are measured in the same manner as parallel drive lines. Remember that in either application, the working angles of the U-joints on a particular propeller shaft must be equal. The calculation of the working angles in the non-parallel drive line is the only difference. The first step is to measure and record the propeller shaft angle. Then check the output flange or yoke for distortion and determine the output shaft centerline angle. The output shaft U-joint working angle can be determined by subtracting the output shaft centerline angle from the propeller shaft angle. In this case, the working angle is 4.5 degrees. Next, check the driven shaft flange or yoke for distortion and measure the driven shaft centerline angle. Determine the driven shaft U-joint working angle by subtracting the propeller shaft angle from the driven shaft centerline angle. Here the working angle is 4.5 degrees. If the U-joint working angles are not within 1/2 degree of each other, the driven component must be adjusted in the same manner described for parallel joint drive lines. Road test the vehicle after any repairs have been made to see if further investigation is needed. For future reference, the formulas for determining the working angles of U-joints are contained in your reference guide. There is one exception to the equal working angle rule. Drive lines that use an odd number of U-joints may not always utilize equal U-joint working angles. The drive shaft angle calculator included in the SuperCom box is designed to calculate the proper U-joint working angles for this type of system. To determine the correct working angle of the center U-joint, set the working angle degree of the forward U-joint, A, at the working angle degree of the rear U-joint, C. Read the correct working angle of the center U-joint, B, at the arrow, plus or minus 3 scale units on the calculator. If the driveline alignment is correct, or if repairs do not solve the problem, balancing the driveline is the next step. It is best to have this done by a machine shop that has dynamic balancing equipment. But if this is not possible, an alternate method is described in Truck Service Manual CTS 2045. Review driveline alignment procedures by completing exercise number 3 in your reference guide. Start the projector when you have finished. Although it may seem time-consuming, You will find that systematic troubleshooting will save both time and money when compared to the guess method. As professional servicemen, you owe it to your customers to use the most accurate, time-saving techniques available. The accompanying SuperCom reference guide includes a quick reference troubleshooting chart for you to use when you have to find and cure driveline vibration.